Hello, welcome to Maths with EJD. I'm still talking about generating functions, and this focus now is on series expansion of generating functions, and this will help us to learn how to expand generating functions into power series to extract coefficients and identify patterns. All right, so we've been dealing with series expansion, but we can keep asking the question, what is a series expansion? What is a series expansion? Okay, we've dealt with this a lot, but let's try to refresh our memories. So a series expansion represents a function as an infinite sum of terms, as an infinite sum of terms. Okay, so for generating functions, a power series expansion helps us obtain the coefficients corresponding to different powers of x, which can then be analyzed for combinatorial or algebraic purposes. All right, so let's take an example to drive home the point like I always like to do. So, example, find the series expansion of e raised to power x squared. So that's what we want to do now, the series expansion of e raised by x squared. So we can say consider consider the generating function. Okay, that's solution, right? Solution. Consider the generating function g of x equals e raised by x squared. Okay, we know that exponential function, the exponential function e raised by t has the well-known, it has the well-known series expansion e raised by t equals summation from n equals 0 to infinity of t raised by n all over n factorial. That's what that looks like generally. So if we substitute, so we can substitute t equals x raised by 2 into the series expansion. Into the series expansion. So that means we have e raised to power x squared equals summation from n equals 0 to infinity. Instead of uh t raised to power n, now we now have x raised to power 2n. You know, this is now our t. all over n factorial. Okay, all over n factorial. So that means we simply have summation from n equals 0 to infinity of x raised to power 2n all over n factorial. I think I want to write this better. N factorial. Okay. So if you do that expansion now, the coefficient of x raised to power 2n in this series is 1 over n factorial. So, I mean, whatever expansion you have, the coefficient is always going to be 1 over n factorial. Okay. So the implication of it is that this means that for each even power of x, we can compute for each even power of x, we can compute the we can compute its 0 factorial, 1 factorial, 2 factorial. So we can compute its corresponding corresponding coefficient by taking the factorial, of half the exponent. Okay. All right, to crown this right, this series expansion is often used in problems involving Gaussian distributions, error functions, or combinatorial identities related to binomial expansions or series summation. Okay, so we come to the end of this particular video. You don't want to miss the next one, which is going to be on multivariate generating functions. So if you have not subscribed to this, if you have subscribed, thank you. If you have not subscribed, go ahead and do that right away. Hit the notification bell so you can always get alerted each time a new video is released. And comment, let me know how helpful these videos are for you. And then let me also know if there's a problem you'd like me to solve or a topic you'd like me to teach. Then like and share so that more people can have access to this great learning. Till I come your way again, keep doing maths right. Bye.